Hey kids, back at it. We're radioactive. Radioactive. Both alpha and beta. Don't matter. The activity of any given nucleus is simply the number that will break per second. All right? It's measured in counts per second, nuclei per second, disintegrations per second, breaks per second, however you care to say it, but the number of those that decide to go through alpha or beta radiation. All right? The more that number is, the scarier it is. All right? The activity of that element is based on two things. One, the number of those nuclei that have the opportunity to break. I mean, this is a spontaneous thing. Again, it's naturally occurring radiation, so it'll just happen. However, if you have 10 pounds of the stuff, they're more likely to have some that break than if you only have 10 grams of the stuff, because simply having a lot of it in one place at one time means the odds of them breaking go up, right? And then, so that N is the number that could potentially break. Now, you can't point to any given one and say that's the one that's going to break, but you can calculate the number that will be breaking. And then lambda is something called a decay constant. Every element has its own decay constant. That rate stays the same no matter how much of that element you have. That decay constant is specific to any given isotope, I should be saying, not element, but isotope of that particular element. All right? So to get the activity, it's just a lambda times an N. Activity is measured in nuclei per second. One nuclei breaking per second is known as a unit called a becquerel. And what you see here is a conversion of becquerels. It is 3.7 times 10 to the 10th BQs, breaks per second. All right, that is what 1 curie is. That is an older unit of measuring the activity, the eagerness of an element to break. All right. It's obviously named after Marie Curie. What would be a very interesting thing for you guys to read is just a little bit about her and her contributions to the study of radiation and the element radium specifically, and the effect that had on her health. In it really is a fascinating story if you wish to read it. Now, what is lambda? All right, lambda is a calculatable number. Again, every element has its own lambda. Every isotope has its own lambda. It's just 0.693 divided by the half-life of that particular isotope in seconds. Now, 0.693, I'm sure you all recognize as the natural log of 2. So for this set of notes, you can just call it that, 0.693, or the natural log of 2, whichever. You notice the title of these notes are in algebra. Okay, so the half-life and activity is based on algebraic calculations, what I will come back with next. Those notes will be in a bit of a calculus perspective, so we'll see where that natural log comes in, but I'm sure you all know it'll be exponential, right? You probably can tell what that's going to be. So anyway, divide that by the half-life. Now, the half-life needs to be measured in seconds for this math to work out. The time required for NO, a number that you originally started with, the number of nuclei, to reduce by half whatever it used to be. Don't matter. So the half-life is the time for N, which is however many you have at any given time, to be the NO, the original number, divided by 2. That's all it is. So the half-life is, again, a self-defining word. How much time do you have to wait for an element to, or a isotope to reduce its number by half? So shorter is scarier, all right? So if I have this pen cap, and this pen cap is radioactive, if it has a half-life of 20 billion years, then I'm probably not too scared of it. That's pretty darn stable. The Earth's only been here about 14-ish, so its half-life is longer than the life of the planet. Now, the other side of that coin is it's probably going to be radiating for a long time, even though it's going to be a very small amount. If this pen cap had a half-life of 10 to the negative 6 seconds or something, then holy cow, that stuff is very eager to decay, very unstable, very just going nuts. And that's obviously bad if you're in the environment. The other side of that coin, the good news is come back in 10 seconds and it'll all be gone because it will have sliced itself in half so many times that it'll be irrelevant. So there's a little bit about the danger comes in because there's a lot of isotopes that have half-lives of months, days, years, decades, centuries, so if things are going to be radiating for an awfully long time, giving off that energy, that's when you have to start getting a little nervous here, all right? This is a data table that is somewhat self-explanatory. If you start at time 0, how much of something you have, the amount of that radioactive element isotope, I just called it 1. It can be 1 anything. It could be 1 pound, 1 kilogram, 1 ounce, 100 pounds, 1,000 kgs, 1 ton. It could be a mole. It could be 10,000 moles, whatever. However, just 1. And how active would it be? I'm just going to make up a number there. Let's say its activity is 1. 1 times 10 to the anything. It doesn't matter. Just call it whatever it is. If I come back at a time that is 1 half-life later, then how much of that something will I have left? Well, all I got to do is take that original amount, multiply it by 1/2, which is 1 over 2 to the 1. Or you can write it as multiply it by 1/2 to the first power. Or you could write it as multiplying it by 2 to the negative 1. It doesn't matter. All of those are synonymous. And what I want you to realize, it will now be half as active as it used to be. That lambda decay constant stayed the same, but remember, you multiply that lambda by the n, the number of those nuclei that have the potential to break. And so the longer it's been breaking, the less active it becomes because it's giving off its energy as it goes. All right. So anyway, it becomes less and less active as time goes by. So if you come back 2 half-lives later, you'll take that original amount, 1 whatever, multiply it by 1 over 2 squared, if you want to write it that way, or if you like to see it better, multiply it by 1/2 in parentheses, but square the 1/2. You're going to multiply it by 1/2 twice. You could write it as 2 to the negative 2 anyway. You guys all know that means you have 1/4 the activity, 1/4 the amount, 1/4 of anything. All right? 3 means you do the same thing. Multiply by 1 over 2 to the third. Multiply by 1/2 to the third. 2 to the negative third. That means you have 1/8 of what you used to have from both a number and an activity standpoint. 1/4. This is obviously then 1/16. All we're doing is slicing it in half and in a half and in a half and in a half and in a half and slice it in half as many times as you have to. Then what I will do is give you some examples of radioactive elements. This is something called gadolinium, and it is what these notes are written for. And this is technical data for gadolinium, and here you see nuclear properties. Some of its half-lives is stable for that particular isotope. What I will refer to or use in this example is the isotope that has a mass of 159. That one. All right? So, if you look to the left, you see 159 GD. Its half-life is 18.4789. H means hours. So 18.5 hours is the half-life of this particular element. Down here it says show decay modes. Well, the mode at which it decays, 100% of the stuff, it's going to break by beta decay. All right? It gives off that much energy, 972.8, and its daughter is 159 TB. That should make sense. 159 TB. So if I want to say that decay products, you can see it only really decays once down there and it becomes stable. So this is one that does have a stable daughter, all right? But it decays by beta. So anyway, that's just a place to look for some other things. Decays by beta. This would be a fantastic review for you to fill in that reaction, wouldn't it? So what we're going to do is with that data there, it's got a half-life of 18.5 hours. I just made this number up, 7.2 times 10 to the 18th. That's a number of nuclei that could be given in grams, and you convert to moles, which your chemistry teacher taught you how to do. You all remember that. And you could then go from moles to nuclei by multiplying by 6 kajillion. It's whatever, but get it into an N. The lambda, remember, what we will get for a lambda is 0.693 divided by the half-life in seconds. The half-life is 18.5 HRSs. Each of those hours have 3,600 seconds in them. All right, so our decay constant for this particular element, here, I'll write it up here a bit. The decay constant for this isotope is 1.04 times 10 to the negative fifth, and that's just per seconds, all right, because that number 693, just a pure number. This denominator, I put it in seconds. I'm not going to convert it. I'm not going to call it a BQ yet because it's just per seconds. I haven't multiplied it by an N. That is going to be the next thing I will do right here. How active is it at the initial? That sub-zero there means at time 0. How active is this stuff? We can calculate its activity by taking that lambda and multiplying it by n sub 0, the initial amount we had. So this is going to be 1.04 times 10 to the negative fifth per second times the number of nuclei we started with, 7.20 times 10 to the 18th. That's a 2 nuclei. All right. That number, the activity sub 0, the activity we started with happens to be 7.49 times 10 to the 13th. That's a lot. BQs. Okay, so it's going to be, you could convert it to curies if you wish. This particular lesson, I just wrote it in becquerels. So that's decays per second. If you had a Geiger counter, that thing would be going nuts, wouldn't it? The NF, the final amount, well, after 148 hours, how much is left? Well, the first thing you got to find out is how many half-lives. How many times do you have to half it? So it was 148 hours, right? And the half-life is 18.5 hours. And if I divide those two, I get the number 8. All right. For the most part, these will be nice, even exponents of 2. Okay. They're usually pretty nice to you. So you're going to slice this sucker in half 8 times. So what you'll do then is you'll say, well, gosh, the NF equals our original amount multiplied by 1/2 8 times. That's an easy way to write it if you want to write it like that, or 1/2 to the 8th, or times 2 to the negative 8th, again, whatever. So that in that final amount after 148 hours, I'm going to take that original, number 7.20 E18, and I'm going to multiply it by 1/2 8 times the final number of nuclei after 18.5 hours. I come back, that number is 2.8 times 10 to the 16th nuclei. We usually just call it N, or you could write out nuclei. So that's our final amount, 2.8 times 10 to the 16th. It's 1/8, or 1/2 to the 8th, 1/2 to the 8th amount of what it used to be. So if you took this number, 7.2 times 10 to the 18th, and just push divide by 2, divide by 2, divide by 2, divide by 2, push that 8 times, I promise that's what you'll get. So how active is it 18.5 hours later? What we will do is take the same lambda, multiply it by the NF. So that lambda again was 1.04 E negative 5. I'm going to multiply it by the new number, 2.8 E16, and that activity is 2.92 E11 BQs. All right, so that's the activity after 18.5 hours. So you can see it lost a lot of activity. All right, it lost 2 exponents, and 3-ish goes into 7.5-ish, 2.5 times? So 2.5-ish 100 times less active 18 and a half hours. So it's getting more and more safe. I still, wouldn't want to be anywhere near it, but slice it in half enough times, I promise it won't be dangerous anymore. But anyway, 15 minutes, yay.